All right, so I just talked about why economics is important. Now I kind of want to go into what kind of skills exactly you will build as an economist. So going off of this last point here about economics being skill building, what kind of skills are you going to use as an economist if you pursue that route, and what kind of things are in an economist's toolbox, so to speak. Okay, so first and foremost, we have logic. So particularly with like those earlier political economists, we talked about how they'll use formal reasoning to approach a problem. And, even though political economics is kind of, become more of a niche field, it's not as popular as it once was. Economists still use logic to, build a theory, to build their hypotheses, and then to kind of mathematically structure their theory if they are doing all theoretical work. And then, of course, if you're not just doing theoretical work, you need logic to have a good test of your hypothesis. But more specifically, when I'm talking about logic here, I'm talking about more the theory and the development of hypotheses. So there are two ways you can develop hypothetical logic. One is called induction, where you start with a theory and you confirm it with evidence. So for instance, if you're like thinking about the minimum wage example again, the prior belief that was held was that, okay, we think that if you raise the minimum wage, you're raising business costs. If you raise business costs above the price of the good, or total cost on average total cost above the price of the good, that'll either shut down businesses or force them to reduce their costs. And if there's no wiggle room on labor costs, they'll either turn away from labor, or they'll have to shut down in some form or another. So that'll increase unemployment. That's your theory, right? So you start with that as your theory, and then you have to use the evidence to either confirm it or deny it. And this goes back to being partially falsifiable from the last slide. Once you have the theory, it's not good enough to just say, I have a theory and stand on it and then have nobody ever test it. If it's not a falsifiable theory, then you can't really say it's a claim towards what reality looks like, because if you can't test it, you can't say it's true or false. Then it just becomes more of an opinion, essentially. So induction will start with the theory, and then you'll do some sort of test, like the Card-Kruger paper that I mentioned earlier, or whatever the hypothesis is. You then develop some sort of test, statistical or experimental or whatever, to either confirm or deny that theory. That is induction. Theory before evidence. Alternatively, you have an approach called deduction as well. Deduction will be like, okay, I'm looking at a list of states that have high unemployment and states that have a high minimum wage. And on two hands, let's say I have, I see like, New Jersey's got high unemployment. New Jersey's got a high minimum wage. Kansas has a high unemployment. Kansas has a high minimum wage. So you're seeing the evidence first, and then you kind of piece together, this looks like it might actually be a trend, right? So you notice a pattern, then you'll confirm it. You'll still have to put it through some rigorous tests, and then you'll use that to develop a theory. So once you see the pattern of, there's high unemployment and high minimum wage, which might not actually be the case in real life, but for the sake of this example, if you see a pattern that says high unemployment, high minimum wage, you'll say, okay, there might be some sort of connection here. Why would that be? Then you'll develop your theory. That's called deduction. The evidence comes before the theory. Both are equally valid approaches. you still have to test both in one way or another. So, just saying that I see a pattern isn't good enough. You'll have to test that the pattern holds up to additional controls. Maybe it's the case that Kansas and New Jersey, those states that I mentioned that might have a high minimum wage and high unemployment, also are, coal, like they also are heavy into coal, which is an industry that's kind of seen a lot of deceleration in the last few years and a lot of downturn, right? It could be that, it could be whatever. You have to develop, once you develop your theory, you have to test it with rigor, right? Otherwise, you're not really doing good economics. So as long as you're testing it with rigor, it doesn't matter if your evidence comes before your theory or your theory comes before evidence. You're still going to have to confirm it at some point or another. So those are the two kind of hypotheses generating and confirming methodology you can do, and they are both ways of approaching an economics problem with your logic first. And then, of course, there are kind of more on the fringe economists who will look at things only using logic. In particular, that guy Ron Paul, the guy I mentioned in the last 2 slides ago, the politician. He is a big fan of that. There's a school called the Austrian School, which looks at economics almost wholly through a logic-based approach. It's called praxeology, and they're looking at the study of how human action will proceed, basically. So if you increase the minimum wage, they might say, humans are less inclined to work the same hours, so we'll be less productive, something like that. I'm not well versed in the Austrian school. Outside of, I know that they're kind of hesitant to use macro modeling, like mathematical modeling, for macroeconomics, because they believe that the macroeconomy is too big to just apply a formula to. And there's some truth to that, in the sense of, in my opinion, macroeconomics does use a lot of high-level assumptions that I'm not sure I fully buy into all the time. But that being said, you can justify an approach based holistically on logic. I think you're going to meet more scrutiny from most academic economists than if you had, a quantitative and mathematical approach with some sort of statistical testing. I think that's kind of more where the field is moving towards, at least for most people. But it's not the whole field. Okay, so the next 3 tools are kind of similar. So I'll start with abstraction. Abstraction is the process of taking a complicated picture, pulling out all the things that are more complex than the question that you're asking, or so complex that you can't come to a clear answer. So if you're looking at macroeconomics, because again, I think that macroeconomics will make a larger assumption base. So if you're looking at macroeconomics, and let's say you're looking at inflation and unemployment, they'll take a representative household in their model. So they'll take a mathematical model, which is a quantitative way of representing reality, or reality, quote unquote, depending on to whom you're speaking. But they'll take a mathematical model, and it'll be based on some abstractions. And an abstraction will be only the key details needed to answer the question. So when you have your mathematical model, they'll look at a representative household, and they'll say, okay, given that the representative household has this budget constraint and these sets of goals, like these objectives, how should they behave? And once they do that, once they determine how the representative household should behave, they'll then do what's called aggregating and scale it up across the total macroeconomy. This approach is, I would say, stylized in the sense of it's very difficult to describe what a representative household is in words. Like you can say like, oh, like the Nielsen data is like, this is the average consumer or whatever, but what does a representative household mean? Are they making the median wage? Are they making the average wage? Those are two very different things because the average wage might be skewed. Are they working one job? Are they working two jobs? And then even once you get like, let's say, a good sampling of what the average household is, after that, does it apply to everybody? If you have the median wage, but you're working one job versus two jobs, is that the same thing for macro purposes, like for the purposes of the question you're trying to answer? It's kind of unclear, and it's determined first by the researcher, and then two by the people who are reviewing the researcher, who are doing the peer reviews, and the people to whom the researcher is presenting, and the level of abstraction, the assumptions that you make, can make or break your paper. So if you do something that's more or less in line with the current research, if you say, okay, I'm taking a representative household, but all these other papers are also taking representative households, sure, that might be a high level of assumption you're making, a high abstraction that you're making. But if everybody else is doing it, it'll probably fly. On the other hand, if you're making an abstraction that's both unrealistic and not really practiced, you'll probably have a tougher time selling your paper to, you're not physically selling your paper, but of getting people to buy into your ideas. So abstraction, to bring it all together, is just the process of making assumptions in order to get at the heart of the issue, so that you're not being so clouded with all these crazy questions that might not really drive your question forward. If you make no abstractions, you're going to lose the forest for the trees. Essentially, you're going to be asking things that don't need to be asked in order to get a comprehensive answer for your question. But if you make too many abstractions and too many assumptions, I use these terms kind of interchangeably, if you use too many assumptions, you'll have an unreasonable paper, and it'll be subject to scrutiny that it might not be able to stand up to. And that, again, that kind of depends on who your audience is, what the question you're trying to answer is, how nice your audience is. Sometimes you'll present a paper and you'll get that one a-hole who wants to tear it down, even though you're making some good, like some decent or standard abstractions. But that's, at the end of the day, that's on you. You got to make the most realistic abstractions, and try to minimize your abstractions when you can. Okay, so the next bullet point I kind of touched on is mathematical modeling. But what that is you have a set of, once you have your abstractions, your set of assumptions that you want to make about the economy or the question you're going to answer or whatever. How do I represent that using symbolic logic? So these all kind of blend together. So by symbolic logic, I mean you set some inflation rate, and you'll set that equal to some variable I, and you set some unemployment rate, you set that equal to some variable U, and you set output equal to some variable Y, and you'll come up with a relationship, like an equational relationship, an equation that says, given Y equals ABC plus D, and given U equals, let's say, X times I, solve for Y in a way that shows the relationship between Y, I, and U. Okay, so and I know that what I just presented was complete garbage. It was just a random set of equations that I just came up with out of thin air. But what I'm driving at is that you can represent the state of an economy abstracted using mathematical logic based on equations. And that's one of the key drivers of economics in 2020. Pretty much everything's going to have a model, whether you're doing theory or statistics at this point, because your theory needs to be backed up using some sort of quantitative logic, unless you're in that one school, basically the Austrian school. You're going to be using quantitative logic to back up your theory, and you want to be able to pin down how variables relate to each other, so how inflation relates to unemployment. And you're going to have some conditions on that. You're going to have, if inflation goes above this threshold, then unemployment will increase. And if inflation stays within this threshold, unemployment will stay the same, but GDP will increase, something like that. And again, this is just a pet example. It's not, what I'm saying isn't, macroeconomics. It's just a random example that I'm pulling from the top of my head. But all this to say that you're going to be representing things using variables, and then once you have the representation and you have a state of conditional equations, how do those variables, you solve them and you see how those variables relate to each other, and then you come up with more precise conditions. So that'll be mathematical modeling, and we'll be doing a lot of that in class. It won't be high-level mathematical modeling, like it's not going to be anything crazy. I'm going to be using real numbers instead of variables. But you'll see it, even like supply and demand is a mathematical model. So if you have an equation, quantity supplied equals 2 times price plus 5. Okay, and then quantity demanded equals negative 2 times price plus 6. You'll have to solve for what's called an equilibrium price and equation. And that's something you'll be doing, starting in week 3 and then pretty much every week thereafter. It's simple. To me, it's simple. Maybe not to a beginner, but it's a simple representation of mathematical modeling. Okay, so, and it's also a representation of abstraction, because you're basically saying price is going to behave in this fashion. If you raise the price by 1, quantity supplied will increase by 2. If you raise the price by 1, quantity demanded will decrease by, I forget what the equation I gave was, but let's say 3. You're abstracting on the overall economy, where in real life, prices aren't so linearly related to quantity supplied and quantity demanded. It's pretty complex to actually get the real, like, truthful statistical quantity supplied and quantity demanded. It takes a couple of years of grad school to be able to really solve for that in a coherent way, but you can kind of ballpark them if you look at data. So that quantity supplied and quantity demanded is an example of using mathematical modeling to build a relationship between price and quantity. It's also a way of looking at an abstraction of how price and quantity relate to each other in the real world. You're kind of simplifying it to something that you in Economics 203 can solve. Okay, you're taking, in my opinion, a great deal of assumptions here in order to say something that you can actually solve, and say something about how a particular market would behave. And then graphing is another way of using mathematical modeling. So you can't really graph without a mathematical relationship, because graphing requires an equation, essentially. But graphing is like the next step down. So you have your logic, you use your logic to build your abstraction, what's important, what's not. Once you have that, you can set a list of characteristic equations that will determine the state of your economy, the state of your market. And then from there, even in academic economics, we'll do some graphing where we might have a supply curve, we might have a demand curve, and we'll look for an equilibrium price. So just kind of doing a pet example here. So let me put on the pen here, and let me change the color. Oh, come on, where is it at? I can't find my mouse. One down. All right, cool. So if this was an in-class session, I would be very adamant in having you reiterate what I'm about to say. So price goes on the y-axis. This here is the y-axis. Quantity goes on the x-axis. That is a Q. It's ugly, but it's a Q. Trust me. Quantity goes on the x-axis. Price goes on the y-axis. Quantity goes on the x-axis. Repeat that bad boy to yourself at home. Price goes on the y-axis. Quantity goes on the x-axis. Price goes on the y-axis. Quantity goes on the x-axis. One more time. Presumably you got it right. I can't hear you because I'm remote. Okay. So I'm going to draw a demand equation here. Supply equation here. Okay. And I'm going to label the supply S, demand D. Okay. So this is two different lines relating to how quantity relates to price. Okay. So let's say like supply is equal to, quantity supplied is equal to 2S plus 2. Quantity demanded is equal to, so you'd say like P price equals, or sorry, you'd say quantity demanded equals 2 times, so it should be negative 2 times P plus 10. Okay, so Q D, oof, it's hard to write here, equals negative 2, that should be a P, plus 10 QS, which stands for quantity supplied, equals positive 2P plus 2. Okay, we can actually solve these equations if you set Q equal to Q and P equal to P. So you're solving for this point here. And if this doesn't make sense, we'll be doing it in a lot more depth a lot of times, but this is just like a sample run for you to see. So let's say we're solving for this point here where you have one Q and one P and they're equal to each other. The price for the supply is equal to the price for the demand. The quantity supplied is equal to quantity demanded. So Q, D equals QS, and then P from this equation equals P from this equation. So you can solve these two equations, QD equals QS, so you can just write them as Q. So Q equals negative, oh geez Louise, it's hard to write. Is there a way to type? There's not. Hold please. I came prepared, guys. All right, can you see this? Okay, so this is a downward sloping curve. What goes on the y-axis is your price. Okay, what goes on the x-axis is your quantity. Okay, the downward sloping one is demand. Okay, and I'm going to say quantity demanded equals negative 2P plus 10. QD equals negative 2P plus 10. It's negative because as the price goes higher, where P is price, as price goes higher, you want less of the good because it's more expensive. Okay, QS is equal to 2P plus 2. Okay, and then it's positive sloping because as the price gets higher, more businesses want to sell the good. Okay, so if I take QS is equal to QD, QS equals QD. It is really hard to find you guys here. QS equals QD. Then I can set these two equations equal to each other. Negative 2P plus 10 is equal to 2P plus 2. Okay. So P is going to be equalized because we're at this point on the graph where the Q's are the same and the P's are the same for both supply and demand. Okay. So I'm going to solve it. I'm going to subtract 2 from both, or I'm going to add 2 to both sides. Sorry. Subtract 2 to, let me restart. I have this equation here, right? I want to add 2p to both sides, okay? Negative 2p plus 2p equals 0. So then I have 10 equals 2p plus 2p equals 4p. So I have 10 equals 4p plus 2. Okay. And then I'm going to subtract 2 from both sides. So 10 minus 2 equals 8. 4p plus 2 minus 2 is just 4p. So you have 8 equals 4p. So p equals 2. Your price is 2. Okay. And then your quantity then will be, so we'll just plug back in the price of 2 into either of these two equations here. So if price is 2, negative 2 times 2 equals 4. So negative 4 plus 10 equals 6. So quantity is going to be equal to 6. And you can check that. 2, we said price equals 2. So 2 times 2 plus 2 equals 6. Okay, so supply equals demand at that point where price equals 2 and quantity equals 6. Okay, so we just solved our first mathematical model using logic and graphing and abstraction, right? Let's bring it all together. The logic was we started with, well, in this case, we're not really confirming anything, but the logic was the mathematical logic that says that, that says that, broadly speaking, if price goes up, you would demand less, right? As things become more expensive, you're less likely to buy it. Not necessarily always the case. We'll talk more about that later, but in general, that should be the case. As price goes up, you'll buy less of a particular item. Okay. We also use logic for the supply curve. As price goes up, businesses want to sell more of the good, right? Or more businesses would enter, and therefore there would be more to sell in that sense. Okay. So that's your kind of like logic that generated some mathematical relationship. But it's not necessarily the case that we went directly from that logic to the mathematical relationship, because we had to abstract in the meantime. What was the abstraction? Well, I just said it, right? One of the things about demand is that in the real world, it's not always the case that as things become more expensive, you demand less. I can think of 100 things where people will buy it because other people bought it because it's expensive. There's a scene in a movie where there's two neighbors and one of them buys an x-ray machine. And the other guy goes, I can't believe he bought an x-ray machine. I'm going to buy an x-ray machine. Kind of like showing off his wealth. And then the other neighbor says, I can't believe he did what I did. I'm going to buy a second x-ray machine. So they keep buying x-ray machines, and it's just like this ridiculous thing where their houses are just filled with x-ray machines. The movie's called The 10. It's awesome. You should watch it, but it's great. At any rate, we call this like conspicuous consumption. It's a case where price might increase, but you'd still buy the good for no real reason, just because you kind of want to show off or I shouldn't say no reason, you want to show off relative to your peers. It's costly signaling, essentially. But, in 90% of markets, that's really not the case. The price of sandwiches go up, you're probably going to buy less sandwiches. I started buying less Grubhub because prices went up. I'm not riding Uber right now, partly because of COVID, which is a price in itself, and partly because actual physical monetary prices went up. So as prices go up, you're going to buy less. But, monetary price isn't the only price, like I just said, and it's not always going to be the case that price goes up, quantity demanded goes down. But at any rate, we need to make an abstraction to say something useful about this market, because, like I said, in 90% of cases, it will be an accurate statement. So anyway, once we made the abstractions, we were able to generate more or less a pretty basic list of mathematical models here. It's a system of two equations that are pretty easy to solve. Maybe harder to solve when you're trying to write it in PowerPoint, but more or less we did it in 4 or 5 steps. So we used mathematical modeling, and then we topped it off by using graphing to kind of just show how the mathematics would apply and where how to represent them, how to represent these equations in kind of I think a little bit more intuitive way of representing them relative to just having the equations. So these all kind of fit in the general economist toolbox. All right. So let's say we have a little bit of data, and we want to test. So we had our logic, we've made our abstractions, we've had our mathematical model, and then we've done a graph. But now we want to say, is this one of the markets where quantity demanded will actually decrease with price? What if we're looking at the market for X-rays, or the market for yachts, or the market for watch Rolexes or whatever, where price increases but quantity demanded will increase because price increased. We could back that up. We could say, all right, well, we have data on different price points and how well they sold, how well this particular market or this particular product sold given those price points. And then we can fit the price points and the price quantity relationship to a curve, basically, where in the real world it might look like this. So this will be your price and your units sold. And we'll say, oh, the actual, sorry, one second. So this is a loss from COVID. I used to be able to just have different whiteboard markers just come up real easily. But let's say the data actually looks like this. We'll use a statistical tool to draw a line that looks more like this. This will be like the line of best fit. It's called a regression line or a trend line. And you might actually have a relationship that says quantity demanded, QD, sorry for kind of jumbling there, QD is equal to positive 2 plus price plus 8. That should be an 8. It looks more like an ampersand. That is an ugly 8. I apologize, but it's an 8. Just deal with it, please. So what if you have statistics, and you do your regressions, you do your tests, and you find out in the real world your demand actually looks more like positive 2p plus 8, right? What does that say? It says that as you increase your price, quantity demanded increases. So if I were a businessman and I were working off the theory alone and untested, I would want to charge a price closer to equilibrium, maybe a little bit higher if the market's not fully in equilibrium. If there's not as many entrants, I can get more of a profit that way, depending on the structure of the demand curve. But I would probably charge closer to equilibrium if I'm just going off the theory. But then someone shows me this data and they say, oh, actually, when you increase the price, quantity demand, it increases. What does that tell me? It tells me I want to increase my price, right? Because the more I increase my price, the more goods I'm going to sell, the more Rolexes or yachts I'm going to sell. And if this is really the relationship, positive 2p plus 8, I'm going to increase my price to infinity because I'm going to sell infinite units, right? Of course, in the real world, it doesn't work like that, but um, given this relationship, I'm going to increase my price until I can't increase it anymore, until I start seeing that quantity demanded increase starts decreasing. So, we'll use statistics. So once we have the theory, and once we've done the mathematical model and the abstractions and looked at the graphs, we'll fit the actual data to the theory, and we'll see, does the theory actually look like the data? And if it doesn't, then you have to retool your theory. Or a lot of economists will massage their data to make it look like the theory. Just, that's the pressures of being in academia. But, I'm kind of kidding. Ideally, you should then retool your theory, come up with a better theory, right? And that's the kind of the purpose of statistics in economics. So, those are like your 5 rule tools that you'll see 95% of the time in economics. Logic to build a theory, abstraction to kind of tease out the most important elements of the theory, mathematical modeling to be able to fit the theory to something testable, some sort of relationship that's quantitative and can be applied to statistics later on, and then graphing to represent the theory in a more appealing way, and then finally statistics to take your mathematical model and see if it actually holds up and if the underlying logic and abstractions hold up given real data. Okay.